Sharp mini-split air conditioner's timer light is continuously blinking, which indicates a communication issue. This could be a problem with its wiring. We also brought the outdoor PCB to inspect it further. It seems like the issue is within the outdoor PCB, so let's test it and see what the problem is. Right now, you can see that I have connected the main power supply. Make sure to connect it very carefully, because if it is connected incorrectly, the PCB could get further damaged. That's why it should be handled with caution. Also, ensure that the reactor is connected along with it. Whenever you work on such circuits, always protect the wires. For example, this wire is currently exposed, but it's not a major issue right now because I haven't removed the PCB from its cover yet. However, as soon as I take the PCB out, the first thing I will do is cover this wire to prevent it from touching any point and causing a short circuit. Now, I will supply direct power to the outdoor PCB. You can see that the connection points are in place, so let's check whether the PCB turns on or not. I am turning on the power now. After switching on the power, there is no sound, no switching noise at all. Normally, when the outdoor PCB powers on, load shifting happens through the relay. Initially, the power goes through the PTC sensor to the bridge rectifier and other components. Once the microcontroller turns on, the load is transferred to the switching relay, allowing the compressor to function smoothly. Since the relay did not turn on, this could mean that the PCB is faulty. Now, let's inspect the PCB to identify the issue preventing it from powering on. I will open the PCB and check for possible faults. This outdoor PCB has two circuits. One is the main circuit, and the other contains the bridge rectifier and IGBTs. I will now open it for inspection. There are two wires, one black and one gray, both labeled with numbers, making it easy to reconnect them properly without any confusion. Here, I see a connector attached, so I will remove it as well. It's now disconnected. Now, why does this PCB have a dual circuit design? One possible reason is the presence of a heat sink. The bridge rectifier is installed here, and a heat sink is used to dissipate heat from both the IPM, Intelligent Power Module, and the bridge rectifier. Additionally, there is another heat sink, which likely helps in dissipating heat from both the bridge rectifier and the IGBTs. So, the purpose of these heat sinks seems to be effective heat dissipation to prevent overheating and ensure stable operation of the components. Now, we will perform a physical inspection of the outdoor PCB, as many issues can be identified through visual examination. The first thing we notice is that the fuse is completely burned. This indicates a potentially serious issue because, under normal conditions, the fuse does not blow. In most cases, when the main fuse burns out, the problem is usually related to the bridge rectifier, a malfunctioning IPM, or a short-circuited capacitor. This is because such failures typically occur on the high side of the circuit, where the IPM and bridge rectifier are located. Similarly, two IGBTs are installed on the small PCB with another bridge rectifier. We will now test these components in diode mode to check their functionality. To begin the testing, we will start with the bridge rectifier, as issues like short circuits in the bridge rectifier, or IPM, usually cause such problems. Upon checking, the bridge rectifier shows a voltage drop of 0.535 volts, which is within the normal range. Testing the next points also shows similar results. Now we will reverse the multimeter probes, placing the positive probe on the positive terminal and the negative probe on the negative terminal. And voltage drop are appearing. It may disappear or it may persist. Now this voltage drop has disappeared. There is no sign of any voltage drop anymore. This means that the bridge rectifier is perfectly fine. Now let's test the IPM. To do this, we will place the positive probe on the positive terminal and the negative probe on the negative terminal. In this condition, there should be no voltage drop or short circuit detected. Next, we will reverse the probes, placing the negative probe on the positive terminal and the positive probe on the negative terminal. Upon testing, the voltage drop is 0.534 volts. Now let's check the W phase, which shows a voltage drop of 0.451 volts. Similarly, the V phase also gives the same reading, and the values remain consistent across all test points. This confirms that both the bridge rectifier and IPM on this PCB are in good condition, meaning there is no fault in these components. Now, let's check this small PCB to identify the issue, because if there is a fault in it, it could also cause a short circuit in the system. We will start with the bridge rectifier by placing the probes in any order, as the main concern is that it should not display 0 short circuit. However, upon testing, it immediately shows 0, indicating a short circuit. Checking the next points also results in 0, confirming that the entire bridge rectifier is short-circuited. Next, we proceed to test the IGBTs, as they are related to the bridge rectifier. Upon checking, they also indicate a short circuit. Moving to the next IGBT, it also shows 0, confirming that all three, the bridge rectifier and both IGBTs, are short-circuited. To further diagnose the issue, we will desolder them one by one to determine the root cause. Sometimes, only one component is faulty, but it causes all three to appear short-circuited. After removing this IGBT, I will test it in the diode mode, and it is completely short-circuited across all points. Next, I will desolder this second IGBT. It seems faulty, but upon testing, it shows a voltage drop of 1.870 volts. Reversing the probes, the reading remains 1.87 volts, which means it is short-circuited because the voltage drop is present across all points. Now, only the bridge rectifier remains to be tested. Checking it directly, it shows a voltage drop of 0.484 volts on one point, and the same 0.484 volts on the next point, which indicates that the bridge rectifier is in good condition. Reversing the probes also confirms that the bridge rectifier is working fine. Whenever I encounter such a situation, I replace both the bridge rectifier and IGBTs, even if the bridge rectifier seems fine, because sometimes a seemingly functional bridge rectifier can still be faulty and cause recurring issues in the PCB. That is why I always follow this practice of replacing both components to ensure a reliable repair. Here is the new bridge rectifier, which we will install in this. So here is its number. This bridge rectifier is approximately 25 amperes. This is a new 20 ampere fuse in my hand. Now, this PCB has 3 additional fuses that need to be checked. These are labeled as FU3, FU5, and a smaller fuse, FU2. I have already tested them, and they are in good condition with no issues. Since all necessary checks are complete, we will now proceed to test the PCB to see if it powers on. Before that, we will clean the PCBs properly. Additionally, there are 4 resistors installed here, and the wire placement points are labeled. The gray wire will be connected to its designated point, the black wire to its respective point, and a connector will also be attached in its place. Now, after connecting all the wires, the PCB is fully assembled and ready for testing. Now, everything is ready, and we will check whether LED 1 starts functioning. If it does, it means the PCB is working correctly. I am now supplying direct power to the PCB, and it has started functioning. The LED 1 is blinking, and the SMPS is now active, which indicates that the PCB is almost fully operational. However, final testing is crucial to confirm that everything is working perfectly. We set the multimeter to DC voltage mode. The negative probe is placed on the negative terminal, and the positive probe on the positive terminal. So, 309 DC volts are appearing here. W 14.16 volts, V 14.16 volts, and same 14.10 volts on the U pin. Since all voltage readings are correct, this confirms that the PCB is fully functional and repaired successfully. Now, let me show you why I always say that a multimeter should not be fully trusted. While 95% of the time it gives accurate readings, there is always a 5% chance that it might not detect certain faults. That's why it's important to use both logic and visual inspection to identify potential issues. Here, I have the same bridge rectifier that I previously tested while it was installed in the system, and at that time, it appeared to be completely fine with no visible faults. However, let's take a closer look to verify if it truly has no issues. I set the multimeter to diode mode and placed the probes on different points of the bridge rectifier. Initially, there was no voltage drop, which seemed normal, but as I continued testing, I noticed that at one point, the reading suddenly dropped to 0, indicating a short circuit. The surprising part is that when I had tested it earlier, while it was still on the PCB, it appeared to be working fine. This is exactly why I never rely entirely on a multimeter reading when diagnosing critical components. Instead, I always remove the component from the circuit and test it separately. Sometimes, I even replace it directly to avoid hidden faults that could cause further damage. If I had simply trusted the multimeter reading without removing the component, I would not have detected this issue. As a result, the newly replaced parts could have also failed. Both the indoor and outdoor units are functioning after installing it back in the customer's unit, and the compressor has successfully turned on, confirming that the repair was completed successfully. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.